This is part 4 of lecture 6. We're going to change gears a little bit and look at a different flavor of algorithm from the exponential mechanism. So the exponential mechanism is a useful general way to define differentially private algorithms. It's often the case that it's like a little hard to kind of wrap your head around what the algorithm is actually doing. It's defined in this very abstract way. And for the case when the set of outcomes is finite, it turns out there's like a much simpler, essentially equivalent way of viewing things. And that's in terms of what's called the report noisy max mechanism. Report noisy max is really a family of mechanisms. I'll tell you a bit about that in a sec, but for now, we'll just think of it as one algorithm. So again, the setup is the same. We've got some set of outcomes. We're going to take them to be finite, so outcomes 1 through D, and a score function that tells us for each data set how much we like each of the outcomes. And our goal is to find an outcome with near maximal score. So the idea of report noisy max is really, like, as an algorithm, it's actually much simpler than the exponential mechanism. So the idea is the following. Here's going to be our algorithm. So our input is x, score, an upper bound on its sensitivity, and a number epsilon. And the idea is all we're going to do is for each possible outcome, we're going to find a noisy score. I'll just call it q tilde of y, which is its score plus some noise. Okay, so plus zy, where the zy's are IID, and they're defined. They come from an exponential distribution. Okay, I'll remind you what that distribution is in a second. And then what we do is we return the y with the noisy, the maximal noisy score. Let's call it like y hat. So it's the value of y in D that maximizes the noisy scores. Okay, so the outcome with highest noisy score. Okay, so this is our algorithm. So the exponential mechanism, it's a distribution on just the exponential distribution, rather. So it's a distribution, this is just a reminder, it's a distribution on non-negative real, so from 0 to infinity. And it has a density function, which with scale lambda looks like this. So let me here, I'll use the y is taken. This is its density. So it's you could describe it as a one-sided Laplace distribution. In fact, usually it's the other way around. The Laplace is thought of as a two-sided exponential distribution. It's got a very simple form. It's easy to work with, and it's well understood how to sample from it. So, so basically what you do is you add noise to each of the scores, and you just pick the outcome that had the highest noisy score. So like suppose our outcomes are we're doing approval voting, so same sort of profile of votes as we had before. So now we'll add a little bit of noise to this count, add a little bit of noise to this count, add a little bit of noise to this count, a little bit of noise to this count, maybe a little more noise to this count, so on and so forth. And then we'll take the outcome in this case would be this third candidate here, because that's the one with the highest noisy score after it, and the highest score after the noise. Okay, so my output would be like 3 in this case. So this is our algorithm. And it turns out that this algorithm satisfies a very similar guarantee. So, turns out the following is true. So on one hand, this algorithm is epsilon differentially private for every score function that is delta sensitive. Okay, so when Q is delta sensitive. And I'm not going to prove that. I'm going to actually leave that. We're going to leave that one as an exercise. But the proof is kind of subtle, but it's a nice thing to work through and to kind of really try to wrap your head around. But the idea is to consider 2 outputs. Y1 and Y2. And look at the probability that you get Y1 on data set X over the probability that you get Y2 on data set X. And compare that to the probability that you get Y1 on data set X prime relative to the probability that you see Y2 on data set X prime. And if you think about, like, what does it take for those events to happen, you can kind of give it some thought and try and understand how to compare those probabilities. So this is going to be an exercise which we'll work through in class. Okay, and so privacy, the privacy is like a little harder to prove for this mechanism than it is for the exponential mechanism. But on the other hand, utility is actually like much easier to understand. So we can consider a proposition kind of like we had for the exponential mechanism. So for all x, we have the following, that if y is the output of the report noisy max mechanism on input x and q and delta and epsilon, again, we get the same sort of statements we had before. So the expectation of q of y is at least q max for this x minus 2 delta over epsilon times log of d plus 1. In fact, the stronger statement is that for all t greater than 0, the probability that q of y is less than q max minus 2 delta over epsilon times log of d plus t. That probability is less than, well, strictly less than, in fact, e to the minus t. Okay, so this, in fact, just follows. So in order to show this, all we have to say is that the noise random variables aren't very big. So this follows from pretty simple tail bounds on the exponential distribution. So here's what we know. So if if z is drawn from like an exponential distribution with parameter lambda, then its expectation is exactly lambda, and the probability, also the probability that it is bigger than some number lambda times t is equal to e to the minus t. And it's pretty much a definition of the exponential distribution. And if z1 to zd are exponential, then we have the following facts. One is that the probability that their maximum exceeds lambda, sorry, the probability that they're, that's hard to read. The probability that their maximum exceeds lambda times log of d plus t. That probability is at most e to the minus t. And a consequence of that is that the expected value of this maximum is less than lambda times log of d plus 1. Okay. You could go and figure out exactly you can get something tighter than +1 there, but you know, that requires a little more work than we're going to feel like doing. Okay, so I'm not going to prove this first bound. This is just the CDF of, these are just standard, you know, exponential. You can look it up on Wikipedia. It's very standard, you know, standard properties of the exponential distribution. I'll prove the second statement just because I think it gives us sort of a useful, the technique can be useful for lots of other problems. So let's just prove, let's call this part 1, part 2. So let's prove 2a. So what we know is that, you know, that the maximum of the z's is like less than something. It's less than this, you know, some quantity, some number. I'll call it like lambda times r. If and only if for all j and d, if each of the z's is less than lambda r. And so then the probability of this happening is equal to, or by the union bound, is at most d times the probability that each of the zj's is less than lambda r. They all have the same distribution, so those d probabilities are all the same. So that's by a union bound. Okay, so that means that the probability that the maximum of the z's is less than I got my less thans and greater thans mixed up. So let me just kind of write this out again quickly. Apologies. The probably that it's greater than this. Sorry, so backtracking a little bit, the probability that the maximum exceeds lambda times log of d plus t So this event happens if and only if there exists some j such that zj is greater than lambda log of d plus t. And so the probability of this event occurring by a union bound is at most d times the probability that any one of the zj's exceeds lambda times log of d plus t. And that probability itself is exactly e to the minus log of d plus t. And that the e to the minus log d is just 1 over d, so that we get exactly e to the minus t. Okay, so that was 2a. In 2b, we're going to use the fact that, following fact, if z is a non-negative random variable, then the expected value of z is the same thing as the integral from z little z equals 0 to infinity of the probability that that the random variable exceeds little z dz. Okay, so this is a nice fact from probability. You can prove that by sort of, it's easier to see why it's true for discrete random variables with sums, but it's sort of a general fact. And it applies both to discrete, as I've written it, it's true for discrete and continuous random variables. Okay, so why does that help us? Well, we're going to apply it to the maximum, right? So let's let z star be the maximum of the zi's. Then the expectation of z star, I'm going to write it as the integral. I'm going to break the integral into 2 parts, from 0 to log d. This is, I guess, times lambda of the probability that z exceeds little z, dz, plus the integral from z equals lambda log d to infinity of the probability that z exceeds z, z star. And actually, I'm just gonna divide everything by lambda because it's gonna make our calculations a little easier. So we don't have to drag lambda around. Okay. So we want to show that the expectation of z star is at most log d plus 1. And then we're going to be able to do that. This first term, the probability is always at most 1. So this is at most the integral from z equals 0 to log d of 1 dz. All right, because that's at most 1. Plus the integral from And I'm gonna pull a change of variables here, and I'm gonna say this is the integral from t equals 0 to infinity of the probability that z star exceeds log of d plus t dz, which we just showed is at most e to the minus t. So this is log of d. This first term is just log of d. Plus the integral from t equals 0 to infinity of e to the minus t dt, and that is just 1. So we get log of t plus 1, and we are happy. That's the end of the proof. Okay, so what have we got? Just that was like a little bit of calculation to bound our the maximum of a bunch of exponential random variables. But it has the consequence that our report noisy max algorithm will do well, and that's because all it's doing is perturbing the counts by these exponential random variables. And so if those perturbations aren't very big, then it's going to give us an approximate winner, and that's all there is to it. So this report noisy max algorithm has the same guarantees as the exponential mechanism. In fact, it is actually very, it is strictly better than the exponential mechanism. It will generally produce like better results than the exponential mechanism, all other things being equal. And that's like not that obvious to see why that is. You could try it with experiments. But there's actually a general fact that can help us understand this, and that comes from the following. Okay, so consider the following. Consider report noisy max Gumball, where we run the report noisy max, but adding Gumball noise to the counts. Okay, so the Gumball distribution is a different probability distribution from the exponential, and it all things being equal, it will produce slightly larger values. So the Gumball distribution, it has support on all of R, not just on the positive part of it. And it has the density I'll just define it this way. It has density e to the minus y plus e to the minus y. So it's kind of a funky distribution. It kind of looks like that. The mode is over here. So it's skewed to the right relative to the origin. And so if we call this the Gumball 1 distribution, then the Gumball lambda distribution is the thing that has been rescaled by lambda. So there you get 1 over lambda so that the integrals work, and e to the minus y over lambda plus e to the minus y over lambda. So it's just like a rescaled version of the original. And then if you add noise, Gumball 2 delta over epsilon to the scores, you get exactly the exponential mechanism. And this trick is also, the exponential mechanism has different names in different fields, but you know, this idea is called the Gumball Max trick. It's used to sample from, for example, softmax distributions that come up in machine learning. It's used to sample from Gibbs distributions that come up in, say, statistical physics and things like that. So it's a trick that comes up in a bunch of areas. All right, so it turns out that report noisy max is very closely related to the exponential mechanism, and that's because the exponential mechanism is a version of report noisy max where we've just changed the noise distribution from exponential to this Gumball distribution. So it's not obvious why one should be like strictly better than the other, but it turns out that the one with exponential noise is generally is going to perform better than the one with Gumball noise, and so it's also just much easier to implement than the general exponential mechanism. Okay, so I'm going to stop there, and I'll see you all in class.